Alright, so for problem 3, we have the French government's looking to build a pipe made of cast iron to transport water across the length of the Garden of Versailles. Given the length of the garden, the density, the viscosity, the diameter, find the pressure drop across the length of the pipe under the following conditions. So first, we're going to go down here. For our knowns, we know our volumetric flow rate, we know our viscosity, diameter, length, porosity, and our density. So we're assuming incompressible fluid. Our properties are known here, properties of water, and from our cast iron as specified in the problem. So our equations are going to be using our continuity, friction factor equations that vary for laminar, turbulent, etc., Bernoulli, and argon for part 2. So for A, we're starting with, we know our volumetric flow rate of 1.2 meters cubed per hour. So from here, we can solve for velocity. Knowing velocity, because we also know our area stated above, we plug into our Reynolds number. With our Reynolds number, we get 2100, meaning the flow is laminar. When we know it's laminar, our fanning friction factor, we just have to do 16 over Reynolds number, and then plug that into our big friction factor to get that value. Then we go on to simplify Bernoulli. We know that our z's cancel out because the same elevation at both points, and our V1 equals V2. This will simplify our pressure drop to be our density times our friction factor calculated above, which we get 0.0028 pascals. So for part B, we're increasing our volumetric flow rate, and from here, same area. From here, we find that our Reynolds number is 5,000, meaning it is turbulent flow. With turbulent flow, we must use a different fanning friction factor equation, as stated over here. We get this fanning friction factor, we can plug that into our big friction factor equation to get a value stated here. So also Bernoulli simplifies the same way, and we know that our pressure drop will equal our density times our friction factor calculated. The change here is that it's 0.0198 pascals, which is a greater pressure drop. So for C, now we know it's a porous media. We're also finding the pressure drop. We know the properties of water and the properties of this material. So from argon equation, we can simplify with horizontal flow and find our Reynolds number to be very small, meaning it's laminar. Bernoulli equation was derived above, and for laminar flow, we know our delta P. We can use this equation here and simplify because we know all of these values as stated below, and we know that would be 709 kPa pressure drop. Alright, so for problem 4, same Garden of Versailles theme. They want to make the Garden of Versailles more exciting, and they want to do ship racing. So this little kid wants to figure out how long it's going to take to get across the race and to find the volumetric flow rate of this water. So we're going to go down here. We have a picture, make it a little more simplified. We know the density of water, density of the boat, the racing, the diameter of the boat, the temperature, the pressure, and given in the equation, we know the net positive section head required equals a net positive section head, which makes our life easier. The density of the air, viscosity of the water. And we're assuming that the ship is a smooth sphere and incompressible. We want to find the volumetric flow rate and the time to travel. So given the properties of air and water from tables known, and the equations that we know is the net positive section head equals the net positive section head required. So this simplifies this equation here for part A, and we know that was given as 3 feet. So what we need to figure out now is our Psat. So Psat at 25 degrees C, which we know the temperature, and from table A9 we can get 0.459 psi. From there, we can simplify this equation above to solve for our velocity. When we know our velocity, we know the area and can get our volumetric flow rate as asked. In part B, we're looking for the time to get across the race. So we know that the weight of the boat is equal to the density of the boat times gravity times volume, which we have everything needed to solve for. And then we know the force of the boat equals the density of air times gravity, times volume of air. So from Stokes' law, we know that Ft equals 3 velocity pi diameter times viscosity. We know that Fd also equals weight minus our force of the boat, which we figured out above. From here, we can isolate our velocity, and doing the correct conversions as well with units, we get 7.18 feet per second. Knowing this, and we know the length of the race, we can figure out it takes 13.91 seconds to get across the race. for problem 5, we're watching an inspiring NASA documentary. You want to build your own torpedo, but you need to figure out how you're going to propel this torpedo. So you get help from Gru from Despicable Me, just because in the movie he seems like he would have all the tools and workspace needed to build said device. You realize you must first build the device to propel it, and your design includes a converging nozzle with an inlet area specified, negligible inlet velocity, and conditions specified as well. Assume the flow is isentropic and calculate the velocity of the exiting air in this device. In this one, we are going over compressible flow. So here's our video. Our known is our temperature, our pressure, area, it's isentropic, and our K value. We're assuming that the pressure at the outlet equals the pressure at the inlet. The air is an ideal gas that's steady state, adiabatic, and no work. We want to find the exit velocity. And our properties known are K equals 1.4. Equations, delta H equals Cp dt. That's just for an ideal gas, and we're assuming air is an ideal gas. And we also know these pressure and exit equations. So first of all, we can simplify. We know that our mass flow rate is equal in the inlet and outlet, so we can cancel that out. We know that the inlet velocity is 0 because it specifies negligible in the problem. We know that GZE equals GZI because it's at the same point, and adiabatic, no work, steady state, so we can cancel out the rest. From here, we know that we get our change in enthalpy equals 1/2 velocity of our exit squared. So we also have this other equation of Cp dt for our delta H. So from here, we just have to find our T exit. So first we start with our P exit. We'd have everything in that equation to solve. Then we plug it into our T exit. We get 375 K to out. Once we have our 375 K as the outlet temperature, we can easily solve for our exit velocity as 388 meters per second. In our last one, we're trying to create a device that moves honey from one beehive contraption to another using a pressure difference at each point. The parallel plates the honey is flowing through are stationary, and you need to calculate the expression and numerical value for the velocity along any point in the contraption, especially at 3 centimeters. This goes over topics 10, 11, and 12, and yes. All right, let's get into it. So here's our picture. We know our diameter, we know our pressure at point 1 and 2, we know our viscosity of the honey, and we know the length that we're figuring this out over. So we're assuming Newtonian, it's constant density, viscosity, there's no electric field, it's fully developed, steady state, no slip at the walls, gravity acts vertically downward, obviously, it's symmetrical, and that the velocity in the y and z direction equals 0 because it is fully developed, and that the velocity with respect x with respect to z equals 0 because it is wide. So we're trying to find the equation for velocity at any point. Our properties know is that honey has a viscosity of 10,000 centipoise. So our equations, we're going to use continuity and Navier-Stokes. Starting with continuity, this guy is actually 0 because it is steady state. Our velocity in the y and z direction are 0 because it is fully developed, so that cancels out the whole term. Knowing this, we know that our change in velocity in the x direction with respect to x equals 0. From here, we can plug into the x momentum balance. We know steady state. From here, we cancel out based on continuity because of our dvx dx equals 0, as stated above. And here we know that our velocity in the y direction is 0 and z direction is 0, but it cancels out the whole term because it is multiplication. And this equals our change in pressure over change in x plus mu. But this can cancel out because if the single derivative is 0, the second derivative will be 0. And then for this guy, we also know that our velocity in x direction is 0 from above, and that gravity works downward. So all of this can simplify, and we're given these boundary conditions. There's no slip at the walls. So we know that at y equals plus or minus d over 2, our velocity is 0 at that point. And based on symmetry, we know at y equals 0, our change in velocity in x direction with respect to a change in y will equal 0. So we can integrate both of these twice, knowing those boundary conditions, and develop a velocity profile in that direction. So if we want to know specifically at 3 centimeters, we just plug in, make sure we have the right units and contraptions, and we get 0.308 meters per second that the honey is flowing at 3 centimeters above the midline.